resonances related to the confinement of the superconducting condensate and increase of PC at that scale, and we have Konstantin as the expert in that field who will talk next. Or these Josephson vortices between the nanoscale islands of superconductivity that were mentioned yesterday, that we modeled some years ago. Of course, there is also unconventional superconductivity. This is an example of ferromagnetic superconductor. I think it's europium-based. So these are ferromagnetic domains inside the superconductor, and they give rise to these vortex loops and this vortex liquid that, under influence of current and field, present very unusual phenomena. And more recently, we worked on hybrids. This is a famous Majorana concept of Kauenhoven lab that Microsoft is pushing for qubit realization. So this is a semiconducting nanowire with a superconductor on top. So we are modeling this type of structures. And as I said, most recently, atomistic simulations after the realization of monolayer superconductivity. This was lead, monolayer of lead on top of silicon. There is a whole flurry of truly two-dimensional superconductors in two-dimensional materials. And that's more the topic of my talk today. So why are we interested in these 2D superconductors? Because we can manipulate them in more ways than one. Mixing and matching different 2D materials and heterostructures is perfectly feasible. Twist between two monolayers of a material induces new phenomena. I'm sure you know about superconductivity emerging in twisted bilayer graphene. Strain, these 2D materials can be strained much more than their bulk counterparts. Thereby, you can affect superconductivity much more than in bulk by using strain. Gating, because the materials are ultra thin, very small voltages will lead to very large electric fields. And very large electric fields can modify your properties of your material dramatically. Right now, I think the record field is about 3 volts per nanometer. And anybody doing calculations will know that that kind of field completely changes the electronic properties of the material. Two-dimensional materials are prone to functionalization and intercalation, so we can functionalize them with different types of adaptants. And altogether, this makes 2D materials ideal platform for computational design. What I forgot to mention is that these are the materials where you can also ideally couple the theory to experiment. So these are crystalline, very nice materials to work with. I will not spend too much time. This is, I think, the only slide or there are a couple of slides in theory, but just to tell you that we need to see the source of superconductivity, we have to calculate the electronic structure, the phonon dispersion, the electron-phonon coupling from first principles. And the electron-phonon coupling will, of course, yield the critical temperature or the strength of superconductivity, if you want. But we need to do anisotropic Eliersberg. We really need to know how much superconductivity we get from each electronic band that is crossing the formula. And this is a very complicated calculation. To give you an example, this is magnesium diboride. This is the structure of magnesium diboride, magnesium planes with boron planes in between. And if you calculate, this is the Fermi surface of this material, and you have the sigma bands, two sheets, cylindrical sheets related to sigma bands, and then the 2 pi sheets here, which are very anisotropic, the blue ones. And these blue ones actually give rise to the superconducting gap at around 3 millielectron volt, and these red ones give superconducting gap at around 7 millielectron volt. So this is an archetypal 2-gap superconductor, and this illustrates you the need for anisotropic Eliersberg calculations to properly characterize which electrons participate in superconductivity and by how much. Okay? So now the question is that we were asking, what happens when we try to thin this material to two-dimensional? So this is what you get for a monolayer magnesium diboride. So again, this is the magnesium atom, these are the boron atoms. The surface band arises. The surface band is related to pz orbitals of magnesium at the top surface. And instead of a 2-gap superconductor, we get a 3-gap superconductor. So this is the pi band gap, this is the sigma band gap, and there is the surface band gap, the third. And these 3 gaps you have to look at this spectrum along this line, persists throughout the temperature range all the way to Tc of about 20 Kelvin in this case. Okay. If we add a layer, if we go to 2 monolayers, everything changes, and these surface gaps, this is now additional surface gap due to boron, they all interconnect into one big anisotropic gap. Although you can separate the origins of superconductivity at different energies, these gaps are interconnected. The same at 4 monolayers, but then at 6 monolayers, again, you start to get a sense of 3-gap superconductivity. So superconductivity changes strongly. From adding 1 layer at a time or 2 layers at a time. And we did the measurement in synchrotron. The samples were grown in Petra Rudolph's lab in Groningen, and in Elettra in Trieste, they measured the surface gap of a 6 monolayer sample, and it ideally matched the prediction of the theory of this purple dashed line here. Quite impressive, actually, with this can be done. Now, what happens when we strain this material? So, when we strain, this is a biaxial strain, so I'm just making these hexagons larger. I'm preserving the symmetry. Bonds will become less stiff. That means lower frequencies of my phonons. So this is the positive tensile strain, red compared to green, shifts to lower energies. You see that? Because of that, the electron-phonon coupling shifts to lower frequencies and becomes larger, just because of this frequency dependence. So basically, I'm increasing superconducting electron-phonon coupling by the axial strain. And if I convert that, this peak is due to the E to G mode. This is the phonon mode that contributes most to superconductivity in this case. And if we plot now what we had for without strain, this was the 3-gap superconductivity monolayer M32 without strain. This is what we had now with strain. So still 3-gap superconductor, but now Tc goes from 20 Kelvin to 53 Kelvin with a reasonable tensile strain of 4. So it exceeds the Tc of the bulk. Actually, this training has been recently realized on these substrates, which by changing the content of different elements, you change the lattice constant of the substrate, and thereby you change the lattice constant of the material that you put on top. Anyway, so strain affects a lot the superconductivity. Now, we wanted to show you some examples on functionalization. So I know you know about hydrides. I'll just quickly mention. This is the famous graph of available superconductors at this time. This is the temperature in the year of discovery. This is my M2 bulk right here, cuprates and ironnictite and so on. But this is the hydrogen sulfide at extremely high pressure that had critical temperature of 205 Kelvin, that was discovered in 2015. And soon later, people went to superhydrides, so having these cages of hydrogen around in this case, lanthanum, that neared the room temperature superconductivity, still at very high pressures. Then some people, not some people, but famous people now in Rochester, Diaz and company, added carbon to this material and claimed room temperature superconductivity was reached. This was retracted. Then they did lutetium hydrides and with some nitrogen dopant earlier this year. That's nearly retracted. None of it has been reproduced in any other lab. So I say they are famous now worldwide. But anyway, it's an interesting field of study. Why hydrogen and why high pressure? Now, we wanted to use this in the context of our 2D materials. So we added hydrogen to MgB2 monolayer. Sorry, this is upside down. So this is boron, this is magnesium, and this is hydrogen right here. And what we get now is this hybridized hydrogen band that crosses the Fermi level and carries a lot of density of states. This is the density of states. There is this one polar singularity that's also very close to the Fermi level. If you could bring this to the Fermi level, you would have even more density of states that contribute to superconductivity. But even as such, hydrogen contributes a lot of electronic states for superconductivity in this But then we also have to remember that hydrogen is light and mobile element. So because it's light and mobile, it mixes the phonon modes of the host material. So these three particular modes of hydrogen mix very well with the other phonon modes of this material. And as a consequence, we get electron-phonon coupling that by far exceeds the electron-phonon coupling of the original MTD2 monolayer. So instead of the three-gap superconductor that we had, now we have single gap, anisotropic, but very high gap. You remember we had 5 to 7 MeV, now we have 12 to 13 MeV. And with strain, we can push this to 70, nearly 70 Kelvin. So this is without strain. This is just before was 20 Kelvin. With hydrogenation, I go to 67 Kelvin just by adding hydrogen. And if then I strain it, I can exceed 100 Kelvin. This is how the PC depends on strain in this material. Now, somebody might say, yes, this is only for this particular material. Well, it's not. This hydrogenation, or as some people call it, phonon doping, has been proven very effective for example, titanium diboride superconductivity. Then in borophane, the borophene is not superconducting. Borophane is superconducting, and it has been recently fabricated in Northwestern University in the US with critical temperatures around 30 Kelvin. Galanine, so gallium monolayer with hydrogen. Galanane is also superconducting with respectable critical temperature of 18 Kelvin. And there's a whole family of MXenes that are just, of course, very hot topic in the community for many functional properties. Well, superconductivity is also one of them. In hydrogenation, especially these materials reach then respectable critical temperature above 30 Kelvin. Okay, now this just goes to show you that small things make a lot of impact in ultra-thin superconductivity. I will just remind you about iron selenide monolayer on SPO substrate that reaches 100 or more Kelvin, double the PC of the bulk material due to the phonons of the substrate in this case. Lead on silicon, I showed you this first example, is superconducting only because of the interlayer electronic states that are forming between lead and silicon. In this case, substrate again is important. There is recent example of chiral superconductivity in a monolayer of tin on top of silicon substrate. Alkali doped graphene. So graphene is not superconducting. You add lithium to it, it becomes superconducting. And then there is also a recent example of tantalum disulfide, which in bulk is superconducting with a lower critical temperature, but as you make it thinner and thinner, the TC goes higher and higher. And this is due to the competition of superconductivity with charge density waves. Charge density waves that are trying to change or reconfigure structurally the material because of the strong electron-phonon coupling are directly competing with superconductivity. So for example, we looked at that, and we looked at defects that arise so when you make this thinner and thinner, you introduce more and more defects in your material. So this was done by exfoliation. So in Manchester, we looked at these defects, and it turned out that these defects are sulfur vacancies. Sulfur vacancies can be healed one way or another. So we checked what are the optimal defects in this material. We found out that if there is, so this is a sulfur vacancy, this is tantalum vacancy, substitution, sorry, this is oxygen substitution, and we found that oxygen substitution is by far the lowest energy. So if there is any oxygen in the system, oxygen will replace sulfur. So oxygen spontaneously fills any sulfur vacancies available in the material. And what is very interesting is that the more oxygen we put, we don't see any difference in the carrier density in the material. The oxygen really heals the carrier density in tantalum disulfide, replacing or filling in the sulfur vacancy. So we have Healing the electronic properties. The carrier density is identical in pristine and oxygenated tantalum. So if we continue calculating electron-phonon interaction, you see that electron-phonon interaction with this lambda increases as we increase the oxygen content in the material. These are the red. This is a pure Janus, so whole one side of the material is made oxygenated. And the critical temperature doubles in this process. And that's part of the reason why this aging effect, which was reported in Manchester, actually is related to oxygenation. So we went on to make a heterostructure that contains monolayers of superconducting tantalum disulfide and monolayers of non-superconducting. So this is the so-called 6R phase of tantalum disulfide. So we have one H monolayer, which is the superconducting layer that I just showed you a moment ago, and one P monolayer, where you can see here the difference where sulfur is sitting with respect to the tantalum, with the difference between one H and one P. Okay. One P is an insulator and presents a charge density wave. One H is a superconductor. So what you get here is a stack of superconducting layers separated by an insulator. And this is basically, these are van der Waals Josephson ideal junctions. This is like a multi-layer structure that can be used for the Josephson devices, which are now the crux of the quantum technology. And these van der Waals Josephson junctions are tunable by strain taking between the layers. Now, this may sound futuristic, but actually it's not. I don't know how much you're familiar with superconducting electronics, but superconducting electronics of the moment is based on multi-layer niobium structures. These are the niobium layers, 100 nanometers thick. When they are brought in proximity, like here, this is where the Josephson junction is created. Okay, so they use multi-layers to use this superconducting electronics. And this is a photomicrograph of a random access memory circuit from Lincoln Lab in MIT, where they reported record density of 4 million Josephson junctions per square centimeter. So manipulating these layers and controlling the coupling between them is crucial for this, and they identified these van der Waals Josephson junctions as the way to go further, the way to go forward. Now, people who have tried to do anything with two-dimensional materials, they will say, yeah, but it's very difficult. If we grow two-dimensional materials on a large scale, we have a lot of defects. If we have flakes, then we have rugged edges and we cannot control how we stack them, etc. Well, that's not true, because just very recently, this is in September, growth of wafer-scale van der Waals superconductor heterostructures has been reported. They had 24 different materials that they stacked at will, and all of them were produced on a wafer scale. So this is an image of pentalayer, if I remember correctly, for the resolution of 5 different two-dimensional superconductors combined into a heterostructure, and they applied a magnetic field and reported current that depends on that field. So all this is coming into play, and all of that can be or may be used in that's me, that may be used in superconducting devices. These were many devices that are possible at the moment. I just want to show you the methodology that we need to model behavior of a superconducting device made of 2D materials or otherwise. It's the time-dependent Ginzburg-Landau framework. This is the core of this Lassé code that I mentioned. We have the first Ginzburg-Landau equation that describes the superconducting order parameter that is connected to the density of our carriers of superconductivity. This is also where the temperature dependencies come into play, and we are not using the standard Wins-Rolando temperature dependence, but the modified one that has been proven to model experiment better at lower temperatures away from PC. Then we have the magnetic field that enters through this magnetic vector potential here. We have disorder that enters through inelastic scattering time here and here. Then the diffusion constant as well, which in case of two-dimensional materials will be directly proportional to the Fermi velocity squared. So all of this can be parameterized from either first principles or from experiments that we are talking about in front. Then we have to solve the second Wins-Rolando equation, which describes the magnetic properties or diamagnetic properties of superconductors. And this is coupled, of course, because this A from here has to be fed back in this first equation. Then we have the current conservation law. So when we apply current to the system, which is what we want to do with your superconductor, electronics, we have to solve for the electrostatic potential. So this electrostatic potential, the temperature is here in the first Wins-Rolando equation. This is also where normal state conductivity enters, which is a parameter from the experiment. And finally, the equation of thermal balance, where we have the time-dependent evolution of temperature, how fast temperature is changing, how far the temperature change is reaching related to conductivity. And these four equations have to be coupled self-consistently. And this is where we enter the external, for example, gating enters here, or thermal excitation in the case of single photon detectors or laser excited superconductivity and so on. So I will stop here. I had one more example that I wanted to show you related to the gating of ultra-thin superconductors. I'll save that for another time. And just leave you with these conclusions that superconductivity in 2D limit offers a very broad scientific play field. So it's not only about superconductivity, but also interplay of superconductivity with other quantum phases. All of that can be controlled by strain, gating, twist, functionalization, heterostructuring. And there are many novel applications underway. So with that, I will thank you for attention and just use the opportunity to congratulate the organizers on having this event again.
Hello. Okay. Morning. Thank you for the interesting talk. I have two questions. The first one is related to the hydride compounds that superconductor under very high pressure, very strong pressure, right? So as far as I know, these compounds are conventional superconductors, right? So there are several things about how can I say to relate or better to show that this material is correspond to the BCS theory. So you make some results that evidence this behavior, this conventional superconductor, perhaps the radio between the critical temperature and the gap, for instance, is 3 point something.
From a computational point of view, so first of all, this is a very old story. So already Ashcroft has shown that metallic hydrogen would be metallic and then superconducting as we increase the pressure. It would be superconducting up to 400 Kelvin. Similar calculations for hydrogen have been done from first principles by Parte and company also years ago. So there's little doubt that this conventional electron-phonon coupling can indeed lead to this high temperature. So that's not really under question here. However, what has been done in experiment doesn't seem to correspond to what the theory predicts. And that's not necessarily a problem, but now most of the things that are being done cannot be reproduced in experiment, and that's the ongoing. So concretely for this lithium hydride, that is the latest discovered in nitrogen vacancies. The group of Lilia Buri has done, just published last month, high throughput calculations of all possible concentrations and things, and they never got higher critical temperature than 100 Kelvin. So, I mean, the answer to your question is it's definitely conventional. That's not the problem.
Okay, okay. My second question is about this compound percent charge density wave phase. I don't know if I understand correctly. You study the structural transition, you construct the phase diagram, or not? You are looking for another thing.
So when you calculate the phonon density of states, you see the structural instability due to the charge density. You can see that. You just have the softening of the phonons.
Nice.
And then depending on where the softening of the phonons is it at M, is it at gamma, where it is, you can reconstruct the lattice that cures that instability.
It's a pure instability,
yes,
right?
Yes,
okay,
exactly.
okay.
So you can guess what should be the reconfiguration of the material in case of charge density.
And
so then we calculate superconductivity before that, and we calculate superconductivity after that. And then we can say whether superconductivity is competing with the charge density wave or maybe not, depending on.
Or coexist or compete or compare, right? And just one, please. Is commensurate?
In this case, it's commensurate because of the small size of our calculation. So we can
Hi, very nice presentation. Mine is a basic question. Somewhere in slide number 21, 22, you showed some 2D materials. So if I am right, yeah, these. So are these 2D materials synthesized?
Yes.
Okay, so how they are related to the superconductivity?
I'm not sure if I understand what you mean.
How the 2D materials are related to the superconductivity?
So the story I was trying to tell here is the hydrogenation.
Okay.
So adding hydrogen to two-dimensional materials, these examples, borophene, pure boron, magnesium diboride, or this titanium diboride, or here gallium, galanine,
okay,
or maxines, different ones, adding hydrogen boosts superconductivity. That was the point that I was trying to make here. Some of them are superconducting without hydrogen, some are not superconducting at all without hydrogen.
Okay.
And hydrogen, as I said, boosts the density of states at the Fermi level because that's what we need. Those are the participating electrons in super pairing. And also mixes up the phonon modes, so by that increases the electron phonon. So this is purely conventional fit. Only talking about electron phonon base.
Okay, great work. Thank you.
I have a question. Magnesium diboride in 6 layers. You showed a plot with the gap versus temperature. Yeah, this one. And we see that the two gaps don't vanish at the same temperature.
Yes.
One is the third and 40. Yeah.
Yes.
Where's the theoretical calculation?
Yes.
Do it. I mean, the experimental one that is kind of surprising, the gap.
Yeah, so I have to, this is gap extracted from ARPES. So in ARPES, they're just following one particular place in the spectrum. What they see there as a function of temperature. So this is not really the gap.
Okay.
So that's why I added here this dashed line. So this dashed line, the purple one, is what corresponds to this experiment. And if you see, it actually doesn't go, it goes down.
Okay.
So it's just following a particular direction in the electronic.
And another question related to thallium disulfide. You showed that as the layers get thinner, it goes shoots up. Could you show the plot? I mean, I want to know. I mean, my question is, what about the estimate for the mean free pair compared to the thickness of? Yeah, you just passed. Yeah, compared to the thickness of the layers. Okay. So that, I mean, what kind of behavior you have it as it gets thinner?
So my guess is, and that's why we did the rest, is that the number of defects per unit cell of the material increases.
So the mean
So the
free
mean
path
free path
increases.
goes shorter.
Shorter, I'm sorry, shorter, yeah.
But that's the guess. They didn't measure it,
Uh-huh.
so I cannot.
Because
They offered several explanations in this particular paper why this thesis should be going up, and the defects are not going up. So
It would be nice to see if there are
would be
shape
nice.
resonances. Okay, so I think the session, over the presentation. Let's thank the speaker again.
thank you.
We call Professor Konstantin Arutyunov from Higher School of Economics in Russia. He'll tell us about fundamental limitations and perspectives of development of nanoelectronics. Floor is yours.
Hello, everybody. While the IT technology is going to be fixed, I start my presentation definitely from thanking the organizers of the conference and particularly the Louis for kind invitation and offering a nice possibility to speak here. So this is kind of a general interest talk where I will outline several points. What are the perspectives and the limitations of developing of quantum nanoelectronics? So I presume I will spend about 5 to 7 minutes on introduction. Then about 15 minutes, I will speak about basic science lying behind these fundamental limitations. And then in the rest 10 to 12 minutes, I will speak about various applications which originate from this story. So as there is word nano in the talk, it's good to start from outlining what scales we're going to speak about. So typically in many cultures, the thinnest object to compare in literature is a human hair. So this is an SEM image of a human hair. It's not a hair, it's my hair covered with gold. But don't be afraid, this is a natural structure of a hair. It's like a pollen-growing creature. So the typical cross-section of a human hair is about from 80 to 100 micrometers. If to reduce by a factor of 10 the dimensions, we're already coming to the scales of, let's say, human blood cells. This is image not of my blood, but just from the internet. If to reduce further the dimensions, we are coming already to scales of organic molecules, few nanometers, and then we have inorganic molecules and atoms. So the stories I'm going to speak about are located here, from few nanometers to few hundreds of nanometers. What about nanotechnology? Let's say nowadays 100 nanometers is already a routine task for electronic lithography. 18 nanometers is already commercial, I mean stress commercial Intel processor, not just a PI announcement. 15 nanometers, you need to be quite an experienced technologist and have good equipment. And everything below 10 nanometers can be considered to be state of the art. So I will speak about how in our lab we developed a method to fabricate sub-10 nanometer structures, and not only to fabricate, but to be capable to reduce the size without damaging the structure. So conventional method is lift-off is E-beam lithography. So we fabricate our nanostructures, for example, like this, and then we want to reduce the characteristic dimension. For example, let's speak about how to make the cross-section of a nanowire smaller. So first, we study the nanostructure with all available analysis, let's say optical microscopy, SEM microscopy. If we do not see any problems, we make a measurement, let's say measuring resistance or IV characteristic at low temperature. Then we take the structure out of our measuring system and put it into ion beam chamber. We wobble it under the very diluted and low energetic ion beam of inert gas. And these are the IFM images of a metallic nanowire on top of an insulating substrate. So everything which is a bright color here is metal, let's say aluminum. Everything which is blue is silicon. So after several sessions of ion milling, you see the cross-section of the nanowire is reduced. And in addition, the inevitable bumps, which you can see here, for example, are disappearing. Typically, I'm asked how the method is invasive or not invasive. Everything depends on the acceleration voltage you apply to in your ion gun. If it is rather small, let's say below 1 kilovolt, so the penetration depth of inert gas atoms inside matrix is very small. It's below 2 nanometers, which is comparable to the chemically damaged surface. So from this point of view, the method of reduction of the dimensions is non-invasive. And other very nice story that whatever you do, in situ fabricated nanostructures always have some surface roughness. But after this ion milling, the surface becomes extremely smooth. For example, this is the AFM scan of the surface of titanium nanowire, and you see that the variation of height is plus minus 1 nanometer. So to finalize this story, we are capable of producing very small nanostructures and non-destructively reduce them down to sub-10 nanometer scales. The smaller cross-sections we obtained were in the range of 4 to 5 nanometers. Now I jump from nanotechnology to big technology. And probably all of us have ever heard about Moore, Gordon Moore, the founder of Intel Corporation. And in early 1965, he formulated the famous Moore's law, stating that number of elements per area on chip doubles every 18 months. Strictly speaking, this is only the first part of the Moore's law. The second states that for any level of the technology, there exists optimum number of logical elements per chip. If it is too small, you are not competitive on the market. If it is too large, the technology is too complicated and you cannot send your processor. And here is the handwriting graph made by Gordon Moore in early 65. So looking at this Gordon's Moore law, one can ask a reasonable question. Is there any limit for miniaturization? And obviously it's not me who asked this question. First time, Gordon Moore himself was asked this question, and he told that in his opinion, approaching 2015-2020, it will be already a collapse of his own law. And indeed, this graph shows that on the age of 1980, 1920, the dependence starts to deviate from this straight line. So one can ask a reasonable question. What are those fundamental limitations which prevent further increase of the integration technology? And in my opinion, there are two main problems. First is quantum effects, and second is self-heating. So now I am going to speak about some basic science behind this statement. And the first question we will discuss, what are, let's say, fundamental limitations for a normal metal wire to conduct electric current? Let's recover conventional textbook quantum mechanics, if one takes a quantum particle and put it in a quantum well of dimensions A and mass of the particle is m, then the energy is quantized. If now to apply the same quantization rule to electrons in a metal, let's take for simplicity the easiest parabolic dependence, then as soon as we start to restrict one dimension, the spectrum starts to be consisting and splitting in different parabolas. And if to stabilize the Fermi energy, this is other story how to do it, I'm not going to expand on it, it appears that each time each size quantized level crosses Fermi energy, we should have some singularity in density of states, which corresponds to increase of the electric conductivity. And another very important story, when the lowest level goes above the Fermi energy, it means that we will have a transition from metal state to insulating state. What are the numbers behind this story? If to put a conventional data for a normal metal, let's say Fermi energy about 1 electrovolt and mass equal to mass of free electron, it appears that the story should be observable in conventional metals with these parameters at a scale of 1 nanometer, which is not very easy to do. But if to think a little bit more and look at this formula, one can understand that other option to obtain this regime of strong quantization is to reduce the mass of the particle. And there are materials which are called semi-metals, and the good representative is bismuth or antimony, where the free electron, where the mass of the charge carriers is by 3 orders smaller than free electron mass. But one should fabricate a single crystalline structure. And we spent about 2 years to fabricate single crystalline bismuth nanostructure on surface of mica. Mica is necessary to make it really crystalline. So that was our working nanostructure, and then we measured the resistance of the central part, reducing the cross-section of the nanowire by our proprietary ion milling method. So theory predicts that when the system approach the level of about 50 nanometers, it should turn from normal metal to insulator. But in between, each time the quantized level crosses the Fermi level, we should have singularity of resistivity. The right plot shows the experimental data, let's say at 4.2 Kelvin, the blue dots, more or less they nicely follow the prediction of the theory, which is dark black line here. So now what about other typical material used in micro fabrication all over the world, semiconductors? First of all, let us suppose that we have a very simple device used in all electronics. Let's say a conductor, which should consist of 2 plates of metal separated by insulation layer. If we want to downscale our object, we should reduce everything, including the red insulating layer. But nature doesn't like this. As soon as the thickness of the insulator starts to be comparable to few nanometers, some pinhole starts to appear. So such capacitor with reduced dimensions will not work anymore as a capacitor. The story is even more dramatic with transistor. Transistor is supposed to conduct or not conduct electric current from emitter to collector, depending on the potential applied on the 3rd base electrode. But there exists a well-known quantum phenomenon which is called quantum tunneling. So when the width of this base electrode starts to be sufficiently small, let's say a few nanometers, electrons will tunnel from left to right and from right to left independently on what potential is applied to the base, so that such ultra-small transistor will not work. So it's a big challenge for technology to overcome these limitations in semiconductors. Even more, if to look at the dependence of the mobility of silicon, which is the most commonly used semiconductor, it appears that, for example, a mobility of charge carriers in the nanowire below 8 nanometers are already smaller than in the bulk. And it's due to problems with electron phonon spectrum in such ultra-small silicon nanowires. So to conclude this part, it appears that various quantum size phenomena suppress electric conductivity, both in normal metals and in semiconductors. And the good, let's say, merit of calculation is about 10 nanometers. Above 10 nanometers, we can consider that still we are in a conventional bulk regime, and below 10 nanometers, we are already approaching this quantum limitation regime. Now let's turn to other technological problem which bothers industrial producers even more than quantum mechanical tunneling. If I made correctly my home exercise, I calculated that for a conventional kitchen heating element with 1 kilowatt power, the volume density and the surface density are about few watts per cubic centimeter, or 6 watts about on 1 square centimeter. Now what about their processors? This level has been already approached about 20 years ago. And now in the modern Xenon processors is more than 100 watts per square centimeter. So locally they are extremely, extremely hot. Nothing will prevent them from melting if to increase the level of integration. Even the water cooling will not work. So the reasonable question to ask, is it possible to get rid out of this Joule heating if to use superconductors? So the question I'm going to answer is, are there any size limitations for dissipation of electric current in a superconducting nanowire? And the story goes to physics of fluctuations. So on this small cartoon, everything which is in a normal state, I will plot in red, everything which is superconducting will be green. So if to speak about the top of the resistive transition, where the system is mainly in the normal state, so the answer is very well known. It's so-called Aslamazov-Larkin correction to electric conductivity, and that was nicely discussed in one of the yesterday's talks. But what about when the system is mainly in the superconducting transition, when here and there fluctuations create normal domain? One should not be an expert in superconductivity, just basic electrotechnical considerations are enough to understand that nothing interesting will happen. Electric current will always follow the green path, just avoiding going into red spots where the resistance is finite. But the story is completely different if we take one-dimensional superconductor. A single domain of a normal metal completely blocks supercurrent. And this will be the subject of the talk related to superconductivity. So how one can understand the finite resistance in a very narrow superconducting nanowire? So theories can show that the energy required to suppress superconductivity is proportional to the free energy per volume. And the minimum volume is the cross-section of the wire times coherence length. And the probability of such a process is exponentially depending on this energy barrier to suppress superconductivity, normalized by some energy. And the whole story is about what is this energy. If to speak about thermal fluctuations, it's just KBT, thermal energy. And it appears that this contribution is important when we speak about temperatures sufficiently close to critical temperature. But there is much more interesting story, because superconducting state is a macroscopically coherent state where the order parameter is itself fluctuating. So, and this contribution of quantum fluctuations is valid for all superconductors, I mean all very thin superconductors, even at very, very low temperatures. So here are the experimental plots we obtained some time ago. Let us, for concreteness, look at the left image, where it is the dependence on resistivity versus temperature for aluminum nanowire. Initially, it was something about 50 nanometers cross-section. Then we reduced the dimension just by 2 nanometers, and we go from black to green dots. Then one more nanometer brown dots. And you might see that there is no way to understand such a behavior using just an Ohm's law. It's just the impact of quantum fluctuations. And for sufficiently thin nanowires, they are not extrapolating to zero. So very narrow superconducting nanowire will never show DC zero resistance. That was aluminum. Right plot shows for titanium, where it is easier to observe on the scales of 30 nanometers. And just to conclude this part of basic science, I can state that quantum size phenomena exist in all solids, whatever you want it or not. It always exists. So it kills good conductivity in normal metals. It reduces the mobility of charge carriers in semiconductors, and it suppresses resistivity in very narrow superconducting nanowires. So from this point of view, one can ask a reasonable question. Is there any future for nanoelectronics? And if to consider it that future is only for reduction of elements, making them more and more compact, the answer is there is no future. This is really very pessimistic prognosis, but I'm quite confident in it. But if to consider that one can anticipate these quantum limitations and use them for next generation of the devices, there might be some interesting applications. So the first application I'm going to speak about a qubit. Now it's a very popular subject. There are numerous suggestions how to make qubits, including optical devices, surface of superfluid helium, and so on so far. Personally, myself, I believe that if to speak about serious work which can be realized and obtained superconducting computer, the elements should be scalable. And for the moment, the only scalable type of the devices are qubits made on superconducting technology. There are two basically different types of qubits superconducting, charge qubits and flux qubits. There are also some hybrids, like for example, fluxonium, but all of them, they can contain tunnel junctions. For example, here it is this region, and here it is this region where there are two Josephson junctions. And it appears that the decoherence time, which should be as long as possible to prevent qubit to contain information, to preserve information, is strongly dependent on the quality of these insulating barriers. And in all of them, there exist so-called two-level fluctuations which kill the coherent state of a qubit. So there is a claim that if one is capable to make a qubit without a tunnel barrier, only using metals, it should have some advantage. The idea was supposed in 2008 by Hans Mui and Yuli Nazarov, and some years later we realized it. So first we published in scientific reports and then in Nature. So we fabricated a horseshoe superconducting contour shortened by a very narrow superconducting wire in the regime of these quantum fluctuations. And indeed, it demonstrated the qubit behavior. So what might be the other interesting device? So-called junctionless transistor. So I think all of you are familiar with the concept of single electron transistor, which consists of an island connected to external world through tunnel barriers with two contacts. And if all this thing is superconducting, very often this device is called Cooper pair box. Once I've heard that Boris Altshuler told that if experimentalist is showing Hamiltonians, something is wrong with the experiment. But nevertheless, I cannot keep myself from not showing two Hamiltonians. And even being a stupid experimentalist, I can notice that Hamiltonians for this device and for the device where the tunnel junctions are substituted by nanowires in the regime of quantum fluctuations are completely identical, parametrically identical. So all physics which is observed in single electron devices, superconducting devices, can be observed in a device where there are no tunnel barriers, but instead there are very tiny nanowires. The only problem that you should fabricate such a structure where the two conjugated parameters, charge and superconducting phase, are conjugated. So if you want to obtain the regime of very strong fluctuations of the phase, you should stabilize the current. And stabilizing the current, it's not just by a good Kisely current source, is to put high resistive or high impedance balancing devices very close to your nanostructure. So that is the structure which was fabricated by us. So the device itself is a very tiny nanowire with cross-section about 25 nanometers, and it was connected to external world by very high ohmic bismuth electrodes. Each of the electrode was about 10 mega ohm resistance. And the RF antenna was used just to pump their high frequencies. A few slides later, I will show why, or to use like a gate to change the mobility of the device. So the IV characteristics looks like this. Black is theory, red is experiment. So it's really weird. It's a superconducting nanowire which demonstrates insulating behavior. Before you apply significant voltage there is no current going through such a superconductor. And this is the result of these quantum fluctuations. Then we fabricated a multi-terminal device consisting of several sections, 1, 2, 3, and all of them, they show the same behavior. So the width of this Coulomb blockade is monitored by application of the external electric potential. It's the left inset, and the whole system doesn't work above the TC of superconducting titanium. So it's really a true manifestation of quantum fluctuations in a superconducting structure. And then finally, probably the most exciting application, in my opinion, is quantum standard of electric current. Let me remind you that nowadays in SI system, the basic unit through which all electromagnetic units are defined is electric current. And in its term, it's defined through amperes interaction of two infinitely long, infinitely narrow wires. You should measure the force, and when the force is equal to something 10 to minus 7 newtons, it means that 1 ampere current is going through. This is very easy to say, but almost impossible to realize in practice with the accuracy necessary for 21st century electronics. So the metrologists are desperate in making the good quality standard of electric current. Another interesting thing that currently, de facto, in modern metrology, there is no standard of electric current. There is quantum standard of electric voltage through Josephson effect, and there is quantum standard of electric resistivity to quantum Hall effect. So they divide one by the other and obtain the definition of the ampere. But as we know, errors are multiplying, so it's not very good. So there is an open question how to create a quantum standard of electric current with required accuracy. And our suggestion is the following. As I showed a couple of slides ago with these Hamiltonians, the two systems, the Josephson junction and the nano-Y in the regime of quantum fluctuations, they're quantum mechanically dual if you change some parameters. So the first IV characteristic shows the conventional IV plot for Josephson junction, and the plot number B is for a nano-Y in the regime of quantum fluctuations. We know that if to apply external high-frequency radiation on a Josephson junction, we will obtain quantized voltage steps, so-called Shapiro effect, which is used exactly for fabrication of quantum standard of electric voltage. So using this duality, one can say that if to apply high-frequency radiation on quantum nano-Y in the regime of quantum fluctuations, there will be quantized steps of current. And this is exactly what we did. So again, our beloved titanium nanowire connected to external world with sets of Josephson junctions to increase the impedance of the system. And when we apply high frequency radiation, quite smooth IV characteristic obtain some singularities. And the arrows show the predicted position of these singularities. So if now to plot the position of these arrows as function of the frequency multiplied by 2E, where E is the elementary charge, it shows the linear dependence, exactly what is predicted. So more or less, this is proof of principle demonstration of a quantum standard of electric current. But obviously, so far, we're not claiming that we made a metrological device. The accuracy of our standard is barely a few percent. And for quantum metrology, one should obtain accuracy at least 10 to minus 7. So there is plenty of room to improve our accuracy and what we are going to work on. And the last slide is not actually mine. It was Professor Pugac, who will arrive on Thursday and will make talk on Friday. She just speak about how information can be transported without any Joule heating, without any dissipation, by exchanging of spins. She had some interesting slides, and her presentation will be related to spin superconducting devices, spintronic superconducting devices. So let me conclude now. What I wanted to tell you, that reduction of dimensions of solids inevitably leads to transition to a new quantum regime, whatever you want it or not. And this sets fundamental limitations to miniaturization of all electronic devices. In each particular case, it's arguable what is the characteristic scale, but roughly it's about 10 nanometers. And if to use this knowledge, one can fabricate quite interesting devices which can be used for next generation of quantum electronics devices. So thank you for listening me. I think there is still room for nanoelectronics to work, and I would like to acknowledge our sponsors who made me possible to come here and to do the basic science. Thank you very much. And while I'm ready to answer your questions, key publications.
Questions?
Thank you very much for your presentation. You told about the electronics,
Yes, sure.
but there is a new word, spintronics.
Yes?
Yes?
Yes, yes. It's
In-
not my field.
Yeah. In this, there is another materials, topological materials.
Yes?
You have to, this is in the substance,
Yes, sure.
but you know,
I was not speaking about topological insulators.
Yeah, the question is if it is the no-go theorem.
Time is running. No, I do not know how to switch it off. Forever I will be woke.
Perhaps in adding to Angelo's question is if it is no-go theorem of the end of electronics could be somehow, we could go around by spintronics or topologies, topological insulators and ideas similar to
You know, as I told, if to consider the progress in electronics only making devices smaller, lighter, then there is no way. We already have obtained kind of the limitation. But if to consider that we can, for example, shift to spintronic devices or more actively use cryocooling, then we go to superconducting devices. There is plenty of interesting things which can be obtained.
Thank you. Any more questions?
Thank you for your talk. Thank you for your talk. It's a quick technical question. On the bismuth nanowires, did you find it difficult to pinch them off? Or are you aided by the quantum size effect? Because as you reduce the chemical potential,
Yeah.
it shifts into the whole band. So you've still got conduction when your electrons are pinched off. Was that a problem? Your slide moved very quickly before I could see.
You mean this transition from metal to insulator?
If you make a 1D wire and you want to pinch it off,
Yeah.
I think, did you say you made narrower wires?
Yes.
Did the chemical potential move down into the valence band under those conditions, or was it the quantum size effect?
Yes, it's exactly what I demonstrated, sure. But in case of bismuth, the chemical potential is fixed by so-called heavy holes. That is why Fermi energy is not changed. Only the potential of electrons is changing. The energy levels of electrons are changing.
Thank you.
There is a question over there.
Thank you. So usually in theory, we have the lower bound to which we can apply, let's say, for example, classical or quantum theory, and that's known as the Planck scale. Do you have in these applications, to which distance you can apply these technological, these technological uses? So what's the minimum scale to which you can use these theories?
You mean the minimum scale?
Yeah, exactly. The minimum scale. Maybe the distance,
Well, it's a
time.
very complicated and difficult question. We are working in so-called mesoscopic limit, when it is not microscopic, so it's not atomical scale, and it's not microscopic. So basically, let's say if to speak about superconductors, the scale should be smaller than the coherence length.
Any more questions?
Just a quick question based on your response. But the coherence length will change if you have high TC superconductors, right?
No, on the contrary, in high TC, coherence length is smaller.
Exactly.
Yes.
So you can make
So
smaller.
that is why I'm mainly working with low TC superconductors like titanium with TC about 0.4 Kelvin, and the coherence length in the dirty limit is about 150 nanometers. But if you want to make this quantum phase effect in high TCs, you should go to 5 nanometers nanowire.
Okay.
That's
Yes.
the problem.
Yeah. Thank you.
It's a universal effect, obviously, but depending on the particular superconductor, you should select the right scale. I'm still finishing.
One last question. I mean, based on the uncertainty principle,
De Broglie wavelengths. Yeah. Yes, sure. Yeah, yes. Yeah. Exactly. So this scale, when the metal goes to insulating state, is more or less with accuracy of some coefficient corresponds to de Broglie wavelengths, which for good metals is about 1-2 nanometers or so.
thank the speaker once
you.
more. And call for the last talk of the session, which is by Professor Isaias Oliveira, Rural Federal University of Rio de Janeiro. He'll tell us about the spike state found in genuine type 1 superconductors.
Hello, everybody. Good morning. Thank you. I will talk about one event. First of all, I would like to thank Professor Luis Valadares for this organization. Thank you so much. Thank you also for inviting me to speak here. One problem. Talk about a metastable state in vortices physics. I would like also many thanks to the LifeMath network. These centers, these universities form the LifeMath. That this university, São Marcos, Universidade Federal de Pernambuco, represented by Professor Albino. Unfortunately, he is not here. My university, not mine, of course, but where I work, Federal Rural University of Rio de Janeiro, also Universidade Nacional de Colômbia, represented here by Ximena and Eliane. Civestap from Mexico, Universidade Nacional de Professor Fermi isn't here also, and Universidade de São Sebastião. and the last one I cannot see. Anyway, I would like to thank all this university and center for compose this life matter. The idea is the connection between researchers and also from America and abroad. Okay, and also the supported from Peru, ProCiencia, Costec, and also again the University of São Marcos. Well, what's happening? Oh, thank you. I will talk about one effect, the spike state. But to talk about the spike states, I would like before show for you other things in order to you understand very well what is this metastable effect. Sorry. Oh, no. No. Okay. Here, the logo of my university, my name, and questions after the talk can be done in Portuguese, Spanish, and English. Okay, not Russian. I'll talk about another work, local rupture of superconductivity. It is because it was done by my two students. They are in undergraduation, and so they calculated so many things. And so I would like to show you that undergraduation students can do science. And about the spike state, the agenda of this talk is the theory used to found this effect, study, and what is the spike state, where it's occur, results in discussions. Okay, thank you. No. Okay, the spike states. Spike states found in genuine type 1 superconductors. Yeah, first of all, what means spike state? I think in the end of this talk, you will know. But what is genuine type 1 superconductor? So I will explain this, and I suppose everybody will understand what means genuine type 1 superconductors. The theory used to study the spike state is the standard time-dependent Ginzburg-Landau theory. You can compare this two equations here used to study this with these two equations showed by Milosevic in your talk. It is so simple in comparison with their equations. Anyway, but it is the theory, the couple of two differential equations come from the free energy of the Ginzburg-Landau theory, the time dependence of the order parameter, the time dependence of the magnetic vector, and it is coupled psi and magnetic field, psi. So you can solve it is in a surface in this case because it reduces a bidimensional problem. Okay, in order to solve these equations, I am using the finite element methods using this console package, and this console has a very nice library of equations, and so you need is write your equations and transform it in the any equations in this package. In order to understand how it is done, I show here these two reference, Sorensen and mine. Okay. It's a long time ago. Okay. Let me show. What is the spike state? The spike state is a metastable state in the vortex physics. For instance, it is a giant vortex state that undergoes a process of deformation after its creation. Bubbles of vortex. I have a giant vortex formed in the center of a needle. We have a mesoscopic needle, and the cross section of this, when the magnetic field is reduced, it means it crosses the normal state to Meissner state. There is a formation, the creation of a giant vortex in this this needle, and so we are studying the cross section of this needle. Okay, bubble of vortex are expelled, forming a new but deformed giant vortex until no one left inside the superconductors. All the magnetic fields will be expelled from the superconductor and expelled by bubble of vortex. If of course, if it has a large vorticity. For a small vorticity, I will show you this giant vortex is expelled in one time. The lifetime of the spike state in the nanosecond scale, it is a very fast effect. So it is a very important point, because to try measure this is not so easy. Here, where does the spike state occur? It's very interesting, because in this I'm come here. The spike state here, the spike state occur in this region, as I told, from normal states. When cross the blue line define the decreasing of the magnetic field. Here is a normal state, and here is the Meissner state. What is Meissner state? What is the genuine type 1? When the superconductor crosses the line from the normal state and go directly to genuine to Meissner state. Let me try explain this diagram. It is applied field. In HC is the critical field. Kappa is the Ginzburg-Landau constant. Everyone knows that the type 1 and type 2 for Buck is divided in the Bogomolny criteria 1 over square root 2. It's about 0.7. Okay. Above 0.7, we have type 2 superconductors. We are interested in study type 1 superconductors. Type 1 bulk materials. Type 1 bulk material is not so poor. It is his magnetic behavior is poor. However, when you are in the mesoscopic scale, it is a very rich physics, as I will show you a little bit about. So it is a phase diagram for a mesoscopic type 1 system, and here we have two critical fields. One is red line is determined when you increase the applied magnetic field. When you increase the applied magnetic field, we reach a critical field. We call it as AC prime, and it has a big jump on the magnetization curve. Magnetization in function of the applied magnetic field. It is the definition of the AC prime. And another critical field is the AC3 prime, when you decreasing the applied magnetic field and reach this field, and it crosses to from normal to superconductor state. Okay, so when I am increasing the applied magnetic field, for instance, I have a superconductor with a Ginzburg-Landau constant 0.5. So increasing the applied field, first of all, forgot when I am increasing the applied magnetic field, forgot this yellow region here, because there is no it, and I am increasing the applied magnetic field. So increasing the applied magnetic field, it is in the Meissner state until it crosses this red line. And when it crosses this red line, it is passed from the superconductor state to normal state. It is, for instance, in this case here is when you see the jump in the magnetization curve, the first jump in the magnetization curve. Well, but when you're decreasing, for instance, in the same material, 0.5, now it is in the normal state. When you now I am, let's suppose, decreasing the applied magnetic field. It's normal states, normal state, normal states. Nothing happened when it crosses again the red line, and it is not new, because it is in Tinkerham textbook. So we cross this line, nothing happened. But when you cross again, this blue line, it goes to a superconductor state, and you can see that it has different critical fields. This critical field destroys the superconductivity, and this critical field creates again the superconductivity states. Okay, we can see that we have the yellow, so you can take others Ginzburg-Landau constants here and analyze the magnetization curves, and you can with this we can divide this yellow region into different many regions. One of them is when you above. We can divide this into regions. One is the intermediate type 1 superconductor. Intermediate type 1 superconductor allows that there is, when you decrease the field, appear vortices inside of them, inside of this kind of the type 1. Type 1, the major of the people talk, no, type 1, there is no vortices inside. Yeah, sorry, bulk materials. But here in the mesoscopic scale, we have vortices there inside of them. When you're decreasing the applied magnetic field, all the magnetic field in the normal state is quantized by the supercurrent around the edge of the sample. In the needle, in the surface is created the currents, and it quantizes the magnetic field inside of this, forming vortices. Okay, but you divide this in this intermediate type 1 and the genuine type 1. Here, and this in the intermediate type 1 superconductor, we have two phases. One when you have the magnetization phase and the magnetic phase. It is important because there is a competition between it's created a giant vortex inside of the needle. opposed to this vortex is one direction, and sorry, and currents, supercurrents are in the edge of the needle is in another direction. So this competition show for us if it is diamagnetic, has a diamagnetic behavior or paramagnetic behavior. Well, so where the question is, where does the spike state occur? Occurs only in the region here, from the normal state to genuine type 1 superconductor. And here I show you as was built the last diagram. It was built using magnetization curves. For instance, here for in the Bogomolny limit, kappa 0.7, 1 over square root 2, we have increasing the applied magnetic field, increasing the magnetization, minus, of course, is a diamagnetic behavior, increasing, and there is a jump. Poof, poof. It is another effect, but I'm not talking about this. But the most important is that we have here the AC prime, where there is a big jump in the magnetization curve. When you reduce the applied magnetic field, and so now in this point it is normal state. When you reduce the applied magnetic field, there is penetration of what's inside of this superconductor needle, and you have these jumps here. Each jumps, like this one, is a fingerprint of the penetration of what's inside of this needle. Okay, and it is go. And so, in this case here, we have a, oh my God, what's happening? Okay, but, well. Dun, 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 dun. Oh, thank you. So we have here the usual behavior, diamagnetic behavior, but in this case, the paramagnetic behavior. So similar, when decreasing the values of the kappa, we can see diamagnetic, paramagnetic, diamagnetic. Sometimes it is diamagnetic and paramagnetic, but in this case we decide that it's paramagnetic because the measure of the magnetization is the diamagnetic behavior. But in this case here, we can see that it is diamagnetic and also diamagnetic response in the magnetization curves. So we can divide that region of the intermediate type 1 superconductor into regions, diamagnetic and paramagnetic. And above this, the limit of the kappa, we found that we have an increasement jump in AC prime and decreasing. However, here in this point, there is a penetration of what when you change the applied magnetic field. So it is not the Meissner state because there is a vortex inside of them, this region, this needle. But here we can see for a very small value of Ginsburg-Landau constant, we can see that increasing the applied magnetic field, we change to normal state, and decreasing the applied magnetic field, there is the transition from the normal to the Meissner state, and both curves is still is the same. Okay. With these calculations, magnetization curves, we could build that diagram. But the important is this transition here. In this transition, when the the applied field reach to this critical field here, this transition is not immediately. There is a time, a lifetime. There is the presence of this metastable state called spike states. Dun, 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 dun. Okay. I can change the slides. No. And we can use it here. Okay, no problem. Thank you. Let me. No, neither here. So, finish my talk. No, this is oh, nice. Okay. Ah, yes. Okay. So this magnetization curve was done for a cylinder square with square cross sections. But I will show two lifetimes. One for circular cross section, a needle with circular cross sections, and another one for triangular cross sections. Well, it is the magnetization curves that I showed you just in the last transparency. Here is okay. In this case here, the Ginzburg-Landau constant in the first in the I can see it very well. In this first graphic A, it is this transition when you have a superconductor with Ginzburg-Landau constant 0.26. The radius of this cylinder, you can see in the figure, is 6 psi and coherent length. I can use? Ah, okay. Okay. Oh, thanks. So, in this case here, it is when you increase the magnetic field, it is there is a jump in the magnetization curves, and the superconductivity is destroyed. When decreasing the applied magnetic field, you reach the AC3 prime, and it goes to a Meissner state. What is happening? It is the map of the psi square, and so here means that we have no superconductivity in the panel A. In this panel, letter A. Blue means magnetic field. It is in normal state. There is no quantization of vortex, quantization of magnetic field here. However, it is what is changed from this to that one is time, just time, because the magnetic field is the same, AC3 prime. In this case, I'm not sure. Anyway, it's not right here, and I don't remember. Sorry, but I decrease in the applied magnetic field, and it is exact determined value. So all inside of this needle we have magnetic field. However, when the time is going, the nucleation of superconductivity is done along of the edge of this cylinder, and this increasing, and it's form a quantization of the magnetic field, or it means the creation of a giant vortex inside of this needle. And in this exact moment, this suffer deformations and expel a bubble of vortex. As you can see, it is the beginning of the process. There is the giant vortex, expel one bubble of vortex here in this point, and it is the vorticity in this case is at about 23. So after some nanoseconds, we have the measure of the needle is superconductor, and there is a giant, small but giant vortex here, spilling another bubble of vortex. You can see the spilling here, and here, and finally we have only one single vortex inside of this needle, and it is spilled, and so we pass here is in the Meissner state. It is, I am in these points, I am here, and after the lifetime of this metastable state, we pass to that point, and we are here. But it is possible to understand only if you use time-dependent Gainsbourg-Landau theory, because you can see the dynamic of the formation of the formation and the creation and the how can I say, creation and the dead of the creation and the annihilation of the giant vortex. Creation and the okay, you can understand. Yeah. So it appears also the same story, but here was calculated to a triangular cross section, and here I'm not using the magnetization curve, but it is similar. Here is the square of the order parameter, like you can find in Tickenham book, textbook. There is no in Tickenham book. Tickenham's introduction to superconductivity, you can see it there, but there is of course not this decreasing of the order parameter when you increase the applied magnetic field, because that is a bulk materials, and this decreasing here is because the boundary effects. Well, but so we have calculated the circular and the triangular cross sections. In the case of, in order to have an idea of the time of this metastable state, I have used the aluminum with the parameters of aluminum. I will show you, not here, but here. Oh, change it. Okay, using the parameters of aluminum, Xi is 1,600 nanometers. Gainsbourg-Landau coupling, this value, of course, lambda is 16 divided is it. Normal resistivity at about 10 up minus 9 ohms meters. Aluminum diffusion coefficient is this, blah, 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 blah. Okay. For circular cross section, the relaxation time in bring by my calculations using finite element method is 36,000 tau, and for triangular is 5,800 tau. What is tau? Tau is the unit of time in the Ginzburg-Landau theory. The D is the coefficient of diffusion, in this case for aluminum. Electrical conductivity, D is the electrical conductivity. So with this, we can calculate the time, because the relaxation time is tau psi square over D. D is diffusion coefficient. Okay, so the lifetime for the circular cross section is 78 nanoseconds, very short effect, and triangular 12 nanoseconds. So we can see that there is a formation of a giant vortex and the annihilation of this giant vortex in a very short time. For circular 78 nanoseconds and triangular 12 nanoseconds. Take-home message is that the spike state is a metastable state with a lifetime in the scale of nanoseconds, and giant vortex created when the magnetic field decreases a certain critical field, and it is spilled in the same fields. It occurs in the transition between the normal state and the marginal states for very small values of the Ginzburg-Landau constant. For these kappa values, superconductors are classified as genuine type 1 superconductors. What is next? First of all, verify this effect using another techniques. And the motivation for me, of course, is motivate my experimentalist friends and no friends also to try and determine these new states. I suppose the bibliography is here, and the second topic I don't have time to talk. Thank you very much.
Say, hello. Hello.
Alô. Alô. Alô.
Ah.
Ah.
Hello? Hello? Hello?
Alô.
Hola. Hello. Now.
Alô.
Hello.
Alô.
Thank you, Isaias, for your nice talk. I have a curiosity about this state. As far as now, you say that this spike state can study or comes naturally, maybe, from the Ginzburg-Landau or time-dependent Ginzburg-Landau theory, right? Do you know if there is we can study this spike state from another phenomenological theory or even from the BCS, perhaps?
I'm not understanding very well your question, but I suppose you're trying to ask if there is another metastable state.
No, see if there is another technique,
another theory. Okay.
For studying.
Yes. Yes. Another theory must be dependent of the time, because if it is not dependent of the time, you cannot see one thing that depends of the time. I suppose this question must be done for Milosevic. To Milosevic, he knows all the theories. My fault, everybody. This work was done in collaboration with some others physics, and one of them is our chairman, Mauro Doria. Sorry, Mauro.
Okay, thank you.
Mauro, if I may, I have a golden mic.
Ah, it's
Uh,
Peru.
Thank you, Cés, for the talk. I was wondering about the comparison of lifetime for the cylindrical and the triangular
Yeah.
shape of the sample. The difference is quite large.
Yeah.
Is that due to geometry or due to the size?
No. The area of this two cross sections is the same. However, the second topic I can explain about this because there is these two different lifetime. It is because the geometry. It is because the geometry. If you have a flat surface, it's easiest to penetration or penetration of what? Transition of what? And if you have a circular cross section, it's more difficult. So to expel what from a needle with a cross section, there is a curvature, it's more difficult than for a flat surface. It will, if I had the opportunity, my students calculate it using London theory. London theory, and it's very easy because yesterday Wilson Ortiz showed the increasement of the density of current when there is a curvature in this device. I calculated this with my students calculated using the simple London theory, and I, of course, used time-dependent Gisborne-London theory. My final point. The lifetime depend of the geometry of the cross section.
It's very interesting because you're suggesting that the Bean-Livingstone barrier depends on the shape of the edge, right?
Yeah.
If I understand correctly. So, yeah, that's very interesting. You mentioned motivating experimentalists to probe this, but you didn't mention a couple of experiments that have been done. I mean, there are experiments on triangular lead crystals back in 2015-16.
Yes, I
Simon
know.
Bending did cylindrical type 1, again lead. And then if you check the numbers for lead compared to the numbers for aluminum, I think you will get longer lifetimes, which again would be interesting or easier in a matter of speaking for experimentalists. So just as a, I mean, just a comment. As a,
thank you. Thank you very much.
Thank you.
We are late on time, so we are going to close the session. Thank Isaias and all the speakers.
Thank you.
To those people who are interested in attending the tour and also the dinner, you can approach the secretary to pay for it. Okay, thank you. Okay, you have some seconds to have some break. Okay.
Thank you. Thank you so much. It's a great pleasure and an honor to be invited to speak at the second meeting of the Latin American sort of community, and where we are allowed to invited rather to contribute. And it's a great pity I cannot be with you there in person this time due to various logistical reasons. So I'm really missing our time in Lima many years ago. And I hope we can continue this series in and around the region. So today I'd like to share some of our both new results and obviously this period of pandemic and various other things allowed for some work to accumulate over these years before since the last meeting. So I want to share with you this work we've been doing on these TMPX3 van der Waals compounds, which are actually have a kind of a in media name, media face. They call as magnetic graphene, and I'll show you how a lot of my current and former students and various colleagues, both in Cambridge and elsewhere, have been involved. And there's some of them who are more directly involved in the data that I'll present today are acknowledged here in the first slide. So I want to start the story more or less where we left it off in the last meeting. I did our conditions with, but here I'm going to face transition. But this is now involved as a phenomenological guide to finding new and different states of matter. And just a very quick review of looking at this axis, those of you new there, hopefully some students and postdocs who are new to the field for their benefit, that we have here a temperature pressure axis. And here the concept is that if there was an ordered state, in our case, we're considering a magnetic order, but it can be charge order, it can be anything. So we think in terms of that how this is the order is nature's way of representing how it loads entropy of a system, and if we can do that artificially by applying pressure, we effectively asking material not to order then, and so that transition temperature reduces to a lower pressure value. Low temperature value rather, and you can play this game till you suppress this ordered state, in our case magnetic one, and then you find all the entropy gets squashed into that corner of the phase diagram, what we call as quantum critical point or quantum phase transition, and many states become equal in energy and can pop out in this region. And the most famous of them is the superconductivity that emerges in this region. And pursuit of this work has led us to finding quite a new set of new things, which I will share with you. So just to highlight that this kind of phenomena is happening not only in the kind of materials that I have measured, but it's broadly conceptually happens as a universality class almost. So you have solid liquid helium transitions you can see here. In organic materials, you see superconductivity, insulating states all being tuned into the critical points and states emerging there. Of course, I'm sure that you hear a lot of discussion regarding high TC or oxide superconductors, but also similar ones now. There are many other ones like pnictite, and so you see this phenomena. And where I started my work was in the area of good metallic magnets, heavy fermion variety, F electron systems of cerium, indium-3 and Ug2, so anti-ferromagnets and ferromagnets. But also these things can happen, as I said, in CDW systems, where you see something similar, suppression of state and superconductivity emerging in that corner. So the two things to kind of focus on for how we progress with this talk today. So the first thing is what I just described, that how superconductivity happens when this state is suppressed, and the nature of fluctuations which emerge, meaning that the ordered state starts to become unstable. It's fluctuating, but fluctuating in a metallic system. So the electrons, as we cool down, and as they lose their thermal characters, primary thermal characteristics, they start to then get scattered by these new fluctuations. So that's the part A of a new physics emergence, and part B is that when these electrons scatter from these fluctuations, they actually damp the fluctuations, and that is how we understand emergence of one side, the non-Fermi liquids, the novel metallic state, and the superconducting state that follows it. So that's the one concept that I want to keep in mind, and that is a very much back of the mind at the moment, and how it guides the new discoveries. The second one is also quite tantalizing one. What you see here is that if you take this cubic compound, cerium-indium-3, you see this behavior that we just discussed in some detail. But if you were to put a layer through this, the system more 2D, and 2D not necessarily only in terms of you have a layered structure, but also in terms of interactions, meaning that if you look at the Fermi surface of this material, this one with a layer, you'll find that it becomes more and more cylindrical. So the 2D characteristics start to become more apparent in electronic properties as well. And you see an interesting comparison here, that you take this material, which is more 2D, and you see the superconductivity emerging, and you'll actually find that it's actually a decade higher, so 10 times more. And you're able to enhance superconductivity in this, going from 3D to 2D. And this was found in these kind of materials on a wide scale. Several other examples were found. For example, here, this is whole series of cerium, cobalt, rhodium, indium. But given that it's a metallic system and it's an F electron system, and energy scales are such that superconductivity happens at quite fundamentally low temperatures, and tunability in some sense is much more viable, because these F electron systems, you get more for your pressure when you squeeze them. But on the other side, the things happen at much lower temperatures, even though we can enhance them quite a bit within that low temperature scales. So we started to imagine quite a while ago now that can we recreate this system, this kind of physics, more or less by hand, rather than relying just on nature to do its job. And the first thing that came to mind was that one has graphite. The graphite intercalates are known to be superconducting, again at very low temperatures. But our story started with us trying to intercalate these materials with magnetic species, which can be tuned. So the idea was that so what we did was we put ytterbium into this, and created a ytterbium C6 compound, and the idea is that arrangement, hexagonal arrangement, will create two opportunities for novel magnetism and possible superconductivity. First scenario being that you have the next nearest neighbor frustration, and that'll create fluctuations in the system. And on the second one is that if you apply pressure, we can tune the ytterbium from 2+ to 3+, and that can lead to, again, more magnetic fluctuations into D layers, and possibly create new superconductivity or other states. So this is what we started with, and in fact, we're quite lucky to say that we found superconductivity happen in C6 ytterbium at very high temperature in that time, and the time being that in that era, and even now, it was one of the highest TC graphite-based superconductor. But the first initial euphoria about finding superconductivity in such a system was quite pleasant, but we couldn't actually understand what was going on, because when we looked at the magnetic data more closely, we found the ytterbium itself was not. It remained in 2+ state and was not magnetic whatsoever. So the magnetism story that I built for you so passionately so far, all of a sudden started to look less and less attractive to explain what happened here. And that to check that, what we found was that we can intercalate the system with calcium, and calcium, which is not magnetic in any way, the TC actually went up from about 6 Kelvin to 12 Kelvin. So this allowed us to rather forced us to rethink the whole picture of quantum criticality and superconductivity in 2D in these kind of systems. And we worked quite closely with our theory DFT colleagues. And what we found was a rather interesting phenomena that in such a system, when you intercalate, what you get is your carbon pi star electrons hybridize with your intercalent d electrons and form what we call an interlayer state. And if interlayer state gets occupied, you can see superconductivity. And if it's not, then and this was something they were able to capture in these calculations, and it's pointed for you. So it's one of the few areas in superconductivity where, given empirical data, the DFT was able to actually more or less predict where you will find superconductivity in these systems, and that kind of holds more or less. So this was all became very big news, and it still kind of holds a record in some sense of this type of materials. However, this leads to a new returning to the original question, that now we have shown that you can tune 2D systems and you can work with them, but we don't have the same magnetic metal and the superconductivity or novel states emerging in the same way as we had seen, say, in much broader set of systems earlier that I showed you in the beginning. And we searched for a while for a viable system where we could do the clean tuning, meaning that the disorder or various other aspects that emerge due to intercalation and making the samples which are air sensitive and many restrictions that came in, we wanted to remove them and return back to working with materials which had, first of all, magnetism, second of all, potential for correlated physics, and third, that they could be tuned towards a critical point or dimensionality crossover. And we were quite lucky to find this TMPX3 family, which I will show a little bit about. But these are generally 2D layers of iron 2 hexagons separated by P2Xe clusters. Then they're generally this kind of a monoclinic structure, and they have weak in-plane van der Waals interactions. In fact, they can be peeled just like graphite into single layers of graphene. Most of them are Mott insulators. So they fitted our requirements quite well in many ways. But there was additional thing that came with them, which is that these materials, which are also quite attractive for the application industry, that they're not air sensitive. So dichalcogenides largely and the your graphite systems are quite air sensitive. These materials are actually generally inert to air, water. And that allowed for kind of experiments which have been not possible in the other system easily to do. So let me just show you how these materials exist. So you have this general family of, for instance, the PS3, iron 3, nickel PS3, manganese PS3. There's some other cobalt and others as well. But these are the ones we have studied in recent days. And this is, you can see how the band gap increases, and that will become relevant in what data I'll show you in a second. We were able to handle them well. We were able to put 4-point contacts onto them, and we're able to just do high pressure experiments, which are often very, very difficult to work to do if you are dealing with a air sensitive material. You have to go to the small scales. Any material, if it's sensitive to environment, will die. Here we have to sit there and build these pressure cells so we can actually do these measurements. And these materials serve that purpose very well. So this is diamond anvil cell work. I can talk more about it, those who are interested regarding the technique. But the initial results were very, very promising. So initially, we saw that you take, this is an insulating part. So we first showing the data on FePS3, so iron, phosphorus, sulfur 3. And we see resistivity versus pressure data here for you. And what you see here is that resistivity kind of acts like a semiconductor or insulator, and normally at reasonable pressures. But then as you increase pressure, you start to see a change in how the form looks like, and eventually it starts to look reasonably metallic down over a wide pressure range, a wide temperature range. But there's also something funny happening at low temperatures, an upturn that emerges, which is to be discussed as we go along. However, what was quite becoming prominent, because these materials have already been shown to be the single layer magnets or magnetic graphene type, a lot of interest was emerging, and people were trying to understand the photonic or electronic properties of these materials as well. So we conducted high pressure, or one could say ultra high pressure diffraction, X-ray diffraction measurements, part diffraction, and we saw some quite intriguing behavior in these materials. And what you will see here is the results of these kind of studies plotted here, and the result. Oops, what's going on here? Yeah. So the results show you that how at zero pressure these are layers, and then you apply pressure, they slide and resettle, and then you go to yet higher pressures, they go through a transition where the bonds reform. So we can go from zero pressure to about 100 kilobars to nearly 180 kilobars. We can see how the material goes from being actually a magnetic insulator to a kind of a metal, and kind of metal we'll discuss a little bit more. So this work's published in 2018. Then we carried out similar structural studies on the full family. So I won't, for the sake of time, I can't show you all of the data. So by showing you just the highlights. So the key thing you see here is that all of these materials have a similar trend. Yeah, they metallize when we see the C-axis collapse that happens. Except the case of VPS3, and I don't have time to go into that. That's the one we're measuring now. But the one that happens in some sense, at the lowest pressure, which is FePS3, metallizes here. It's something we'll discuss more, but this is a general trend in this family. So there's a quite rich lot of work to be done, and we're showing you some early one here. Here is the 4-point proper data, and here comes some nice hints for interesting correlated physics. Yeah. So first of all, if you remember, and these are Mott insulators, so we're expecting the kind of metal that emerge will show some sort of correlations. And as I mentioned earlier in the beginning, that how if you have a quantum critical point type of system, and right now I'm going to speculate a lot because we have only early evidence. So bear with me, and it's a thought process. Maybe we can later emerge to a conclusion on these things. So what we think is happening is that the antiferromagnetic system in that material, when we apply pressure, goes through a transition, and the magnetic order becomes unstable as it crosses the boundary, and then we have short-range magnetic order in the system. And that, so when the system becomes metallic, it forms the Fermi surface, those electrons then start to see those fluctuations, and they scatter off those fluctuations, creating a very unusual type of, very similar to the strange metal ITC type of state when the system becomes metallic. So that's kind of a summarize here. That here you are. This is the insulating state yet, and this is system. You can see the big drop that happens. The system becomes more metallic above 124 kilobars in this data, and you can see we see the 4/3 power law. So if it was a normal Fermi liquid, you would expect to see a T square power law here, but you see due to the 4/3 power law here. And yet there is still that case at lowest temperature we have that upturn. What does that? What is that one? We don't know yet. But most initial ideas are that could that be some kind of a Kondo coherence type setting in which would be quite unusual in a D-type D-metal system of this type with very light masses. But these are again some evidence, new behavior coming out of I would say quite challenging experiments. These are we're doing 4-point resistivity under fairly hydrostatic condition. Then we're also doing X-ray synchrotron work for the structural side to map onto this the electronic properties. But magnetic properties, how they're directly evolving, obviously it's very difficult to do that at lab-based experiment and these pressures, not because of the pressures so much, but because the moments are pretty small and samples are pretty small. So magnetometry of normal kind, gives and you see lots of features and cannot be sure which one is true or not. So the one real robust tool, of course, is neutron scattering. And so we conducted, at least in our kind of correlated world, perhaps the highest pressure neutron experiment, about again 180 kilobars, and we were able to follow this shift from the magnetic propagation vectors from 0.1/2 to 0.10, and this again, this is a talk by itself to go into the details of this data, but it's published in the PhysRevX in 2021. It shows that how system evolves from this insulating magnetic insulator to a magnetic metal. And this was very much a big news at the time because this kind of experiment hadn't been done. So ILL, where the experiments were done in France and Grenoble, they put it on their website as the highlight for quite a while. But that is what it is, and here is the summary of that. All of those data. So here we have the pressure versus temperature phase diagram, and so first of all, we did do some lab-based measurements of magnetism under pressure, and you see some data, but we could only go down to quite early part of this phase diagram, meaning right here, and that's well before any transition could happen. But what we can establish is that it's a proper antiferromagnet there with neutrons. We could establish what were the propagation vectors in insulating state, and then we apply pressure. As I told you, when the layers slide against each other and reform, you see the first phase area, and then they still remain fully magnetic, but the transition is actually strengthening, goes up a little bit, and then comes the van der Waals collapse, and system becomes metallic. But also within that, and the previous slide I showed you that you have short-range magnetic order which emerges in this space. So that by itself is very interesting. Now, just returning to the original question very briefly, the original question being that what about superconductivity? So we do have a hint of non-normal or abnormal or special or strange normal state, but in this material so far, superconductivity has not been observed, and there can be several reasons for that emerging. One could be that upturn that happens at lower temperature, and perhaps we need to go to higher pressures. Perhaps we need to go to lower temperatures than we have, and all of that is being done. But what is quite tantalizing is that you have a neighboring material. So this is sulfur 3. If you go to selenium-3, you actually see that exactly at this kind of a pressure, it follows more or less the same story. But when this collapse happens, it becomes superconducting. And we have been investigating this as well. And so far, our neutron and structural work shows that this material probably loses magnetism. Unlike this one, which retains short-range magnetism, this one loses magnetism and goes superconducting. This could be a simple explanation, but there could be more evolved way of thinking about it, and that since the size of the atom, sulfur versus selenium, the odd thing that happens here is, so you go from a 2D insulator to a more 3D metal, because van der Waals collapse makes it more 3D. So the fact that this material perhaps becomes 3D more quickly before the 2D nature of the system can find superconductivity in itself, while this can happen in this material, but we still have magnetism to explain. So this is still an exciting area to investigate, and that's what we're doing. So this is to just give you kind of a summary of so we have done all of this work that I showed you in FEPS3. Currently we're investigating other ones and see if they can become metallic or superconducting, or can we say that there is something about the physics of the sulfur compounds versus selenium compound, because the recently another selenium version was shown to, I think it was nickel system was shown to be superconducting. How we can explain that, I think that's the work for the future, to be presented at the future conferences. Just for fun, I wanted to also show you, while we are setting up our pressure cells, we find that this, as the band gap closes, there are quite radical color changes in the material as it goes forward. So there is other interest that's evolving, and how that represents the electronic subsystem that evolves with pressure in these system and allows for such properties to emerge from the photonic side. I'm not a photonics person, not our lab, but these things we see as a side product of what we're doing, and we'll begin to think about these as well. So I will just end there and thank. It requires a lot of collaboration, a lot of goodwill and patience from many different people, and so I'm just so I will stop there with this current presentation. Thank you.
Thank you, Mont. Okay. Who would like to ask a question first? Make yourself known if you'd like to.
It was a great. Hola. Hello.
Hello. Sorry, I can't hear you very well.
It was a great presentation. I understand that there are two kinds of transitions: the metal to insulator transitions, and the mod insulator to charge transfer insulator transition. How happened this transition between mod insulator to charge transfer insulator?
I don't think maybe I misspoke. I don't think we have shown or seen any evidence of transfer from a mod to a charge insulator transfer. It's just that when I used that word was that in some of these materials start out as charge transfer insulators, and we have not picked them. We are just working with the one which are mod. So we're only seeing a mod insulator to a metal transition so far. And those, maybe we'll look at those in future, but we haven't yet studied any. There was a speculation early on that the nickel version is a charge transfer insulator, but neither the DFT nor transport supports that. But then it would be starting with the charge transfer insulator. So I'm afraid I have to disappoint you. Don't have much to say about that.
Thank you. Who else would like to ask a question? Okay. Well, that leaves it to me to ask a question. I'd like to ask an experimental question. Could you tell us about the pressure medium? Does the pressure change with temperature as you cool it down? Does the pressure change in any way? And also with that, does the glycerin form a glass, or is it just, how does the glycerin freeze? Does that change how you interpret the pressure or the measurement?
Very, very, very important point. And this, we have to kind of clean the data for it. So what we had been, so let me just say more general thing around that. So since we did quite a wide variety of experiments, meaning that there were transport experiments, there were synchrotron experiments, and there were neutron experiments. And we were able to then consider different pressure medium and how they both either facilitate or obstruct our understanding of the data. So so first of all, to answer directly your question about the glycerol one. So glycerol actually it's a quite interesting physics by itself. But fortunately, since we're using the glycerol for transport measurement, whether it becomes a glass or not doesn't actually hinder interpretation of our data. And what we monitor is that is it still hydrostatic or not? And the way we monitor that is by two scales. So first is that we put we have three scales, or three, how to say, indicators. So one is we put a lead or a tin sample as an additional sample to look at superconductivity as a manometer, which second is we put a bit of ruby in there to look at its ruby fluorescence and the material itself as we accumulate data. So the sharpness of the transitions in each case or otherwise broadening gives a good indication whether we have hydrostaticity in the system or not. And I'll push back to rather pull back to address more the other aspect of your question. So we then try to see in a synchrotron data set what does this do. And we found that although hydrostaticity is not affected, it certainly does look to start more glassy, especially if you and depending on how you cool the system, and X-ray data starts to become very difficult to do. So for X-ray work, we eventually mostly used either helium or argon as pressure mediums, which do not cause that problem. Yeah, so that's
thank you. That answers the question very well. If there are no further questions, your last opportunity to ask a question, then let's thank the speaker, please.
Thank you. Thank you. Sorry to miss you all over there. Have fun.
Thank you. Do we have the next speaker available?
Daniel Cornejo. Daniel Cornejo está acá. Daniel Cornejo is present here. Daniel Cornejo from Brazil. I think he is absent. I think he's absent. No, so in that case, we are going to cut to go to have lunch. But I would like to give some instruction at the end. Okay.
Thank you, Liz. So no further talk this morning.
No, the next talk.
Okay.
Okay. Well, some announcement before going to have lunch. First of all, about the speaker, Pratap Kollu is going to give a lecture for the students. The students were not here in the morning. He's moving his lecture for tomorrow very early in the morning. I will say in Spanish as well in order that the students understand. Los estudiantes están invitados a participar al curso que está dando el profesor Pratap Kollu mañana 8:20 de la mañana. Bien, llegar puntuales, por favor. El profesor Pratap Kollu está dando un curso, ya 8:20 de la mañana. Okay. Also, I think that in the afternoon we have speaker Mario Reis from Brazil. I think it's around here, right? Mario is around here. Mario Reis, right? Oh, okay. Mario is invited. I think that if you stay for a while in a moment, because you need to coordinate with our team managers in order to check how they are to connect after lunch. Okay. Nice. Also, those people who are registered for the tour will be you need to be gathered here tomorrow at 10 to 1, 10 to 1, so 12:50. And for the dinner will be on Friday, will be gathered here at 5 p.m. Okay, when it is the last talk, after the last talk, there will be some buses. And about the photography, some photos of the event will be 2 times. Tomorrow, on Thursdays. On Thursday will be here and also outside in where it says University of San Marcos. Okay. Well, I think that Professor Bustamante wants to say something else. No. Okay. Well, now we are going to gather here again at 2 p.m. Okay. Thank you.